Hi, Professor. I was just going over. I'm having trouble with the number five recitation,
Uh-huh.
and I was just wondering what part of the chapter two or three it like goes over predicting um, the reactions.
Oh, which reactions are we talking about?
Like just for example, like the one that we did on recitation, an aqueous solution of iron three nitrate is mixed with an aqueous solution of sodium hydroxide to form a precipitate.
Mm-hmm.
So is there like in the chapters that goes over like step by step, like how it does in the book from moles to grams and like how it breaks it down step
Well,
by
that's a really
step?
good point. I will find the part of the book. We basically we talked about it in class, but that's a good plan. I will dig out the appropriate part of the book where you can go over it at your own pace. Thanks for
Okay,
pointing that out.
thank you.
So you're basically looking for how you can predict whether or not precipitates are going to be formed.
Yeah, and it like a good example is like if you go in the actual textbook, page 99, is it just says deriving moles from grams and it has like step by step. And
Mm-hmm.
that's kind of what I was just looking for, if there's something like that at all.
Well, grams, I mean, that particular reaction, we're not really dealing with grams and moles. I mean,
No, I think
that would just be predicting how much
yeah, I was just
precipitate would
more
form.
in the sense of like giving an example of like how it breaks it down step by step on that page.
Okay.
Not really. Yeah, I was just wondering, is there like something like that in the book? Because I was trying to look through the chapters and I really didn't find anything like that.
So is the question like why does this precipitate and this doesn't?
Yeah, and also like how do I know how many moles is gonna like it's gonna dissolve into? Am I getting that from the subscript of the iron three nitrate?
Yeah, you get it from the formula. The formula tells you how many atoms are present in that molecule, and then you just basically look up the molar mass of each one of those atoms, and that tells you the molar mass of the molecule.
Okay. Can I talk to you after class? I don't want to hold up
Sure.
lecture.
Yeah, no
Okay.
problem. Yeah, no worries. Yeah, it's got a couple of good questions already. Anything else people want to talk about before we get going? I'm going to try, hopefully, fingers crossed, to try and make some sense of all this nonsense today. Since we've been talking about all this sort of far out stuff, I want to sort of relate it back to the periodic table, and hopefully it'll start to make a little bit of sense. Because it was pointed out to me yesterday that yeah, it doesn't make a whole hell of a lot of sense right now. And believe me, I feel you. So I just basically I'll pick up from where we left off on Tuesday and then try and relate it to some actual chemistry, which is what the hell we're supposed to be doing here. So no other questions before we get going? Okay. Let's get back to Schrodinger's kitty. Okay. So like I said, what I really want to get to is the electronic structure of atoms, because that is the key to the whole thing. What we're trying to figure out now is that since Bohr showed how hydrogen could work, but nothing else could, and then Schrodinger came along and showed how every other atom could work. But with Schrodinger's explanation, we had to deal with all this sort of crazy shapes of where we would find electrons. Bohr said we would just find electrons simply in circular orbits around the nucleus, and that isn't the case. They form all these sort of really bizarre orbits around the nucleus. So we're going to sort of look into that a little bit more today, and then relate it to see, well, does this have some sort of real life application? Because right now I ain't seeing it. So, and I get you. So let's just quickly review some of the shapes, because remember there was four numbers that we had. There was basically a zip code, an address for every single electron. The first one was how far away is it, the shell. First one was the shell. How far away is that electron from the nucleus? Is it close, number 1 or 2, 3, 4, 5, however. Then there was subshells after that. Subshells were these weird shapes inside each energy level or shell where we would find electrons. And then the orbitals were the actual physical places where electrons will be put. And we can only put 2 electrons in each one. So these were the different subshells. We remembered that special puppies deserve food, and that's how we remembered there's S, P, D, and F. S had only space for 2 electrons. There's only 1 orbital, and it's a circle or a sphere. And then P, there's now places for 1, 2, 3. Every time we move up 1, we gain another 2 orbitals. So S has 1, P has now 2 more, D has 5, 2 more, and then F has 7, 2 more. So each time we're adding 2. So S, P, D, and F. And if I prefer special puppies deserve food. You can use whatever memory trick you want in order to remember them. And then remember, these are different shapes. That is basically all these are about. Different shapes that Schrodinger's wave equations predicted. So L is that number. First we have N, that's the shell. L is the shape, that's the subshell. And then we figure out inside that where the electrons are. So each value of L is just a letter that designates the shape. And it's 0, 1, 2, and 3. S is 0, P is 1, D is 2, F is 3. And you'll see why we use 0, 1, 2, and 3 in a second. And then these are the shapes. S is easy to remember because S is spherical. Spherical starts with an S, so there you go. Completely spherical, and there's space for 2 electrons. This is the lowest energy subshell, is S. That's the very first place when electrons move to a new level, a new shell. This is the first place they're put, and we're going to get to that in a second, the order in which we put these electrons in, because that's really critical to understanding the chemistry. P has, as I mentioned before, 3 places to put electrons. Remember, we keep adding 2 every time we go up a level. S is 1, P is 3. And so this leads us to this number. Let me be able to draw here. Here we go. So M to the L, if you remember, that is the name of the orbitals themselves. So N is the shell. L is the subshell, S, P, D, or F. So that will be 0, 1, 2, or 3. And M to the L tells us exactly where in that subshell it is. M sub L. And we get it by looking at L. And so since P is 1, we can immediately figure out how many places there's got to be, how many orbitals there are based on this number. We go from negative L to positive L. So we start at negative L. So L is equal to 1. So negative L is minus 1. Next would be 0. And then the biggest number can be plus 1. These actually are physical places where we can put electrons. This is one place. This is another place. This is the third place. There's 3 of them. And so there's room for 6 electrons. Okay. And this is, and if you remember, this is what they look like. Remember, they sort of have that dumbbell shape. And in the middle, we said that there was something called a node. And a node is where there's no probability of there being an electron. Well, this is where the nucleus is. So the electrons are going to be on one side or the other side, in either the X direction, the Y direction, or the Z direction, up and down, in and out, side to side. Although usually we think of Z as coming in and out rather than Y, but they're all 90 degrees to each other, okay? Then we get to d orbitals. Now L is equal to 2. So because L is equal to 2, our m to the L is going to be from -2 to +2. What's in between -2 and +2? Well, -1, 0, +1, +2. So that's 1, 2, 3, 4, 5 places to put electrons. So there must be space for 10 electrons. Since each one, these are orbitals, remember. Orbitals have a place for 2 electrons each. So there's 5 of them. And so there's a total room for 10, okay? That is our d orbital. And the d orbitals have a kind of a weird, much weirder shape. They look like this. So instead of like a balloon with 2 lobes in it, now we have 4 lobes in it. One, whoops, let me go back. 1, 2, 3, 4. Now the weird sort of the thing that's like a little crazy about this, there's still only 2 electrons there. It looks like there should be room for 4, but these are individual orbitals and there's only room for 2. So we'd have 1 here and 1 there. And the last shape, so this is 1, 2, 3, 4, 5. Remember, we can also think of these as -2, -1, 0, +1, +2. That's what those numbers mean. That's what the M to the L means. It designates each one of these individual shapes. So the first 4 sort of, I don't know, makes some sense. And then this last one is a really weird looking shape. Yes, Nicholas.
So these d orbitals have individual shapes?
Mm-hmm.
Okay.
They all have different shapes. So S is spherical. P has those 2 lobes, looks like a dumbbell. And these are what the Ds look like. Now the d orbitals, 4 of them look very similar, but the 5th one looks different. So I don't want you to get all hung up on that. Just think of that there's 5 of them. And the other thing to remember is that they all have equal energy to each other. That'll become important when we start filling them up one by one. I just want to give you an idea of sort of what they look like. The shape is really only important for S and P because that's what we're going to be dealing with when we get into bonding. We look at how electrons are shared. D, not so much because D, we're not going to be, the shape of d orbitals mainly has to do with transition metals. And we're going to talk a little bit about transition metals, but we're not going to spend a whole lot of time on
Is it the problem of projection?
Excuse me?
Is it the shape difference because of the projection?
Projection?
Like it projected a different way. I mean,
the shapes are very important later when we talk about how well electrons in outer levels are protected from being pulled one way or another. We'll find out that the shapes have a lot to do with that. Different orbitals can protect the outer shell electrons, which remember are the valence electrons, the ones involved in bonding. The shapes of the orbitals inside will determine how much they're pulled toward the nucleus or how well they're able to be taken away by non-metals. But that's coming down. That's coming down the line. We're not going to think about that right now. But yeah, the shape, obviously these shapes are important, but I just want to focus on S and P right now. And then the F orbitals, then we get into the the really weird stuff. So remember, L equals 3 now. And so m to the L is going to be from -3 to +3. And what's in between? -2, -1, 0, +1, +2. So there's 1, 2, 3, 4, 5, 6, 7 places to put electrons, 7 orbitals. And since there's 7 orbitals, there's now room for 14 electrons. And that's the biggest orbital. It's really the biggest subshell. There's only 4, S, P, D, and F, which has 1, 2, 3, or 1, 3, 5, 7 places to put electrons. And each of those places is an orbital, and they each have room for 2 electrons. This is the highest energy subshell of them all. F is the highest. Once you fill up F, you go to a new energy level. You go to a new shell once F is all filled up. And so these have some crazy shapes. Let's have a look at some of these. I just like looking at these because they're kind of crazy. So look at these. I mean, these, some of them sort of like, they look like the sort of the 8-lobed, look like some crazy thing like a clown would make at a children's birthday party, you know, stretching the balloons together. And then these other ones sort of look like top hats. And then this one is just completely insane. But all you have to remember is there's 7 of them. They all have equal energy, and they get filled one at a time. And we're going to go into how the electrons fill them one at a time, and try and relate that to the periodic table.
Still 2 electrons, each one?
Excuse me. Yes, Nick, you got a question?
Yeah, I know you said don't get hung up on it. I'm just,
But you're hung up on it, I can tell.
yeah, I'm just making sure. So we don't have to like memorize every shape in orbital F, every shape in orbital D. We just have to know that they have the same energy level.
No, I just find it amusing that you know, Schrodinger came up with all this. It must have, like, can you imagine the first time he like presented his findings at a meeting or something? Everyone's sort of staring at him, going, "Uh-huh." And so two electrons are moving around in this shape. Sure. Yeah. Oh, that makes perfect sense, Werner, you know? So yeah, I just find it funny. The thing is that, you know, the S and the P, when you think of those shapes, you can easily relate them to the actual chemistry of bonding. And we're going to do that later. When we show that when 2 atoms bond with each other, what happens is that these orbitals overlap with each other, and atoms whose orbitals overlap very well form strong bonds, and atoms whose orbitals don't overlap as well form weaker bonds. That makes sense. And really, we're just going to look at the overlap of S and P orbitals. We're not going to really deal with D and F quite as much. So
Okay.
yeah, so remember S, remember P. Excuse me. The other 2 we're not going to focus on as much. That would be if you're going to take a more advanced class. Oh dear, a more advanced class on inorganic chemistry. You would spend a lot more time on D and F orbitals, because it's the transition metals where the differences in energy between F and D orbitals are very, very small, and electrons can jump back and forth. That explains why transition metals have different valences, where they have different numbers of charges, because their electrons could organize themselves in either the D or the F, and they move back and forth, because, like I said, the difference in energy is very, very small once you get out there. And so we're going to talk a little bit about that, but the shapes of them in particular won't be that important for this particular class. Later classes, sure. So yeah, so don't spend hours and hours in bed, you know, memorizing the different shapes, because I certainly don't. And you're not gonna have, you know, draw these on an exam. I don't you know, draw the S, draw the P, but D and F is, yeah, that's a little beyond my ability to draw, believe me. I can barely draw a stick figure. So this will give you an idea. I think this is where we left off last class. How many electrons are in each particular shell? So the first shell, there's only an S orbital. Remember, as we go up, so here's our N. N equals 1, 2, 3, 4. So that's the shell. That's the distance away from the nucleus. Every time we go up, we add a subshell. So the first shell, 1, only has one subshell, S. That's it. That's the only, so once you have your 2 electrons in that shell, you're done. And you move to the next shell. So this particular shell would be hydrogen and helium. Hydrogen has 1 electron, helium has 2. That's it. Then we move to N equals 2. Now that we've moved to the second shell, it has 2 subshells, S and P. And now we have room for, S has 2, P has 6. We have room for 8 electrons. So once we get to 10 electrons, the first shell and the second shell are completely filled. Then we move to the third one. Now, the third shell has room for 1, 2, 3 subshells, S, P, and D. S has 2, P has 6, D has 10. So that would be 18 more. So now that we've added another 18 electrons, now 1 is filled, second shell's filled, third shell's filled. We move to the fourth shell. And now the fourth shell has room for 4 subshells. We just keep adding 4 subshells. So it has all of them. It has S, P, D, and F. So again, 2, 6, 10, and F has 7. Remember, S has 7 orbitals with a total capacity for 14 electrons for a total of 32. So once we've added another 32 electrons, then we move to the 5th and then the 6th. So the total number of orbitals within a shell equals the shell number squared. 1 is 1, 2 is 4, or 3 is 9, 4 is 16. And each orbital has room for 2. So the number of electrons is 2n squared, because there's 2 electrons for every orbital. Okay? So this just gives you the overall numbers. Now, what's really important is how we fill each one, because that is really all about the chemistry. Any questions so far? I know it's just still not making much sense, but I think we're going to hopefully turn the corner into where this is actually related to something. Because right now it just seems like a lot of just crazy information that you have to remember. But I promise you, it will all make sense in a second.
No more than F.
No. There may be, I mean, theoretically there might be, but these 4 subshells are all we need in order to define all the elements we have so far. So I think I mentioned a class or 2 ago, as we make more and more elements, there may be like a G subshell or an H subshell, but we haven't got there yet. So we'd have to make some element that's really big that has 180 electrons in it or something, and see how it's organized. But right now we haven't found an element that requires any more. So it's our take-home message. I love take-home messages because it's the only one people remember. So 4 numbers. N, how far away from the nucleus are you? That's either the energy level or the shell. They're called both. That's our principle. So that's our energy level. Second L, that tells you which subshell it is, what shape. So the first one, how far away from the nucleus are we? Second one, what shape is it when it's in that particular shell? Third one, what's the orbital? S has 1, P has 3, D has 5, S has 7. Which one is it? And we'll show that as we add electrons, it's important that we fill them in the right order. And then finally, we can only have 2 electrons in an orbital. That's it. The first one that goes in always has an up spin, so plus 1/2. The second one into the orbital, we always say it has a down spin, or minus 1/2. That's it. That's the only thing you have to remember about spin. And as I pointed out, it's the spin of the electrons that's involved in magnetism. It's why some elements are permanent magnets and some aren't. We'll go over that. Okay. So this is our review of this. Probably a good thing to keep in mind. As we go, every shell adds a new subshell. So 1 has only 1. 2 has 2, 3 has 3, 4 has 4, and 5 has 4, and 6 has 4, and 7 has 4. So 4, S, P, D, and F, as Raymond asked before, are there any more subshells? Not so far. 4 explains all the elements we found so far. So this is what we call the different subshells. We give them a name. First, where are they? What shape? Where are they? What shape? And then this is the address of each individual orbital inside that subshell. So S, there's only one place to put electrons, and we give that a 0. 0 is always the one in the middle. You can see 0 is always in the middle. And we just keep adding an orbital to one side of it, negative, and an orbital to the other side of it, positive. That's why we always increase the number of orbitals by 2. 1, 3, 5, 7. Because we add 1 to the positive side, we add 1 to the negative side. So this gives you the number of orbitals in total, and then how many are in the complete energy level. And remember, the number of electrons is exactly twice this number, because there's 2 electrons per. So what does this have to do with anything? These all have different energies. As I mentioned before, S has the lowest energy. And then we go to P, and then we go to D, and then F has the highest energy. So as we fill electrons in, as we're making new elements, we're filling in, we're adding more electrons all the time. This is the order that they get filled in. We start with 1s at the very bottom. That puts in 2. Then we move up the ladder, and we put 2 in 2s, and we move up some more, and we get to 2p, and you put 6 in there, and we go up to 3s, we put 2 in there. And you can see as we go higher and higher, the difference in energy becomes smaller and smaller. And think about it, there's 2 changes in energy we're talking about. One are these subshells, S being the lowest, P being next, D being next, F being next. But we're also talking about energy levels in the shells themselves. 1, 2, 3, 4. So notice as we get really high up, like these much bigger atoms with lots and lots of electrons, the difference in energies, 1, are really, really small. And 2, sometimes a higher level will get filled before a lower one. So you can see here that
4s.
that 7s, we put electrons in 7s before we put electrons in 5f. Because F is such a much higher energy level than S, that even though 7s is further away from the nucleus, it's actually lower energy. And this will become important, like I mentioned before, with transition metals. transition metals will move electrons from F to P and S way out in these outer levels. And when they move the electrons around, they get different charges. They give away either 1 or 3 or 5 or 6 electrons, depending on what the differences in the energy levels are. And this explains how they can do that. So you may be asking yourself, how the hell am I going to remember all these orders? Because this is important. The order that we fill in electrons is really important. And I'm saying, no, you don't have to remember this, because there's this easy way to do it. And I'll show you the trick for doing this.
No.
So this is the way to get around all that and remember. So the order that we put them in, we just make this box here. Make a little box, and we put our energy levels 1, 2, 3, 4, 5, 6, 7 on the left, and on the top we put our orbitals S, P, D, and F, and we just write them out. So 1 has only S, 2 has S and P, 3 has S, P, and D, 4 has S, P, D, and F. And then when you want to remember the order that they get filled, what we do is just make diagonal arrows going down this way. 1, 2, 3, 4. And that gives you the order. So 1s comes first, and then we go back for the second arrow. 2s comes next, and then we come back and make another arrow. Oh, and then 2p, and then 3s, and then we come back for that arrow for the next one. And oh, and then 3d, 4p, 5s, and then we come around again. That's how we get the order down. So you don't have to memorize this. Just make this table. Either you can memorize the table. I can't even memorize the table. I just write out the table every time I have to do this. And that gives me the order. So this is the order that they're filled in. 1s, 2s, 2p, 3s, 3p, 4s. And so far, it makes sense. We're going up one at a time. Okay, it makes perfect sense. But notice 3d gets filled before 4p. That starts to, since the energy, as we go further and further away, the energy levels get smaller and smaller and smaller, and then they start to overlap a little bit. And so in order to remember this, I make this diagram. So any questions about making the diagram? And when you, if you're wondering, like, you know, what do you mean by order? As we add electrons to elements, this is the order in which they're added. So, and I'll show you how that works in a second, but this is the order when we're building atoms, basically, and we want to know where the electrons are. This is the order that they're added. And I'll show you, it explains their chemical behavior, okay? Let me give you an example. Here's phosphorus. So we look up phosphorus in our periodic table, and we see it has, what's its atomic number? What's the atomic number of phosphorus?
15.
15. So a neutral atom will have 15 protons and the same number of electrons. So it's got to have 15 electrons. So let's fill in how we would add the 15 electrons. The first two, oops, let me go back. The first two go in 1s. We come back. Where's the next one go? 2s, okay? And then 2p, 3s. And then we come back. Nope, move these around. And then we come back. So our first two, 1s. So we go, there's 2 electrons in there. So we call it 1s, and there's 2 electrons in that particular subshell. shell, subshell, number of electrons in it. Next is level 2, second shell. First subshell in there is S, and there's 2 electrons in it. Second subshell in the second shell is P, and there's 6 electrons in it. So far, we've dealt with 2 plus 2 plus 6. That's 10 electrons, and so I have 5 left. So after 2p is 3s. That's the shell, that's the subshell, that's the number of electrons in it. What's after 3s? We go all the way back around again. All right, 3p. So shell, subshell, how many electrons are there? What number would I put by the p?
Three.
3, right. Because I've got 2 plus 2 plus 6 plus 2, that's 12, and I got 3 left. So I would put 3 there. And that is what we would call the electron configuration of phosphorus. This is called the electron configuration because these are how its electrons are configured in the atom. Where are they? We're going to do another a way of showing the electrons called an energy or orbital diagram, which gives you even more information. Not only will it show you where they are, but it'll give you the relative energies of the electrons as well. The configuration just tells you where they are, okay? And so we use this in order to figure out in what order do we put them, okay? So let's clear that. So these are some of the rules we're going to use when we're making these configurations. Now there's 2 sort of basic rules. Aufbau, which you can probably tell was a German, came up with that one. Now electrons are always placed in the lowest energy subshell that's available. Yes, Nick.
I know this is just, I think, to do with neutrons, but do isotopes have different configurations?
They do not.
Okay.
Because isotopes have the same number of protons.
Protons, okay.
Neutrons do not change the nucleus's charge. And so if they don't change the charge, they're not going to change the number of electrons. Yeah, so neutrons are not involved. So carbon 12, carbon 13, carbon 14 will all have the same electron configuration. Yeah, good question. So Aufbau says, always, when it's time to add another electron, where am I going to put it? You always put it in the lowest energy subshell available. So hydrogen, duh, there's like the very lowest subshell is 1s. That's as low as it gets. Well, that's where the electron goes. Where does the next one go? It would go in also 1s because it's still room for an electron and it's the lowest energy possible. And so the second rule, the Pauli exclusion rule, says that sure, you can put another electron in there because it's the lowest energy available, but it's got to have a different spin. The 2 spins can't be the same. They have to spin differently. They would balance each other out. So the first one goes in with an up spin, or plus 1/2, and the second one goes in and has to have a minus 1/2, or down spin. So you can only have 2 electrons in there. There's only room for 2, and they have to have opposite spins. So one more rule. Hund's rule. Good old Hund. So Hund specifies that if you have orbitals of equal energy available, like for instance, a p orbital has, or p subshell has 1, 2, 3 orbitals, right? So here we've got 3 orbitals in p. How do we fill them? Well, there's a number of ways we could. So let's draw our box for p. Now remember, this is -1, that's 0, and that's plus 1. That's where those numbers come in really handy. That's the M to the L. That tells you where inside that subshell the electrons would be. So our first electron would go here, pointing up. Now Hund says the second electron can't go in that first orbital. It's got to go to another one. And when you think about it, that makes sense because remember, electrons are all negatively charged. They want to be as far away from each other as they can. They repel each other. So they're not going to pair up until they absolutely have to. They're not going to pair up. They're going to be spread out far away. That's lower energy. When you start pushing them together, they repel each other. That's going to be higher energy. So the way we fill up these orbitals is we fill them up one at a time. So 1, 2, 3, and then only after each one of those orbitals is half filled, then we start to fully fill any of them. So then the fourth one would go here. And then the fifth one would go there, and then the sixth one would go there. This will be important when we're dealing with magnetism later on. Because if we have a lot of unpaired electrons in a subshell, it becomes magnetic because we have a whole lot of electrons all spinning in the same direction. And that becomes a magnetic element. If they're all paired up, it's not magnetic. So that'll be important when we're dealing with magnetism. So Hund says if we have if we have a subshell with a lot of orbitals, we fill them up one at a time. And the same is true for D. D has 5. 1, 2, 3, 4, 5. So we would fill it up 1, 2, 3, 4, 5, and then go back. So the sixth one would finally be put 6, 7, 8, 9, 10. So always one at a time. Fill them out. Electrons are negative. They want to be as far apart from each other as they can, physically in space. And then only when there's no more room, the N is half filled, and then we fill it completely. Okay?
So
Yes.
there are more magnetic elements than non-magnetic elements?
No, most elements are not magnetic.
Okay.
Yeah, so you need to have at least 2 or 3 unpaired electrons for it to really be magnetic. And then once you have like 4 or 5, then it's very, very magnetic.
Okay.
Yeah. But most have 1 at 1 or 2, and they're not terribly magnetic.
Okay.
So this is how we fill them up, one at a time. This is like the first 10 elements. Or actually yeah. So hydrogen, helium are just filling up the 1s here. And then we show how we add them one at a time. So lithium, so the next element to be added, the next electron to be added, goes into the next shell and the lowest energy subshell, which is S. And then we fill in the second one, and then we start to fill in the P. 1, 2, 3, and then oxygen. We now have 4 electrons in the P, so now we half fill this one, then we half fill this one, and then neon is completely filled. See if you notice a pattern here. Lithium always has a +1 charge. Where do you think that which electron do you think is given away?
2s.
Yeah, it's this electron. This electron right here is the one that's given away. So then lithium has a full shell. There's a completely filled shell, and it looks like helium. Beryllium always has a +2 charge, or it shares 2 electrons. And when it does that, it also looks like helium. helium without a charge. And then we get down to carbon. Carbon has 4 electrons in its outermost shell, which is 2. It's got these 2, 1, 2, 3, 4. It makes 4 bonds. Nitrogen has 5 electrons, 1, 2, 3, 4, 5. It needs only 3 more electrons to have a full shell. Well, guess how many bonds it makes? 3. Oxygen has room for 2 electrons in its outermost shell. Well, what's the charge on oxygen when it's an ion? When oxygen becomes an oxide ion, what charge does it have?
-2.
And where do you think those 2 electrons go?
2py, 2pz.
Mm-hmm. So it needs 2 electrons to have a completely filled outer shell. When it has a completely filled outer shell, it looks like neon, which has a completely filled first shell and a completely filled second shell. Both are completely filled, and that is a stable configuration. Fluorine has only room for 1 more electron in its outermost shell. And so it pulls and pulls and pulls and pulls until it gets an electron from somebody else and then fills it. And then it looks like neon. So basically what the story of chemistry is that all these elements want to get to a noble gas configuration. They want to look like neon. Yes.
Could you just explain again why carbon couldn't lose 2 electrons?
It could, if it does form an ion, it loses 4 electrons. It gains 4 electrons if it becomes an ion.
Why it wouldn't only lose the p shell?
Because then it still doesn't have a full shell. They want a full, each element wants to have a complete shell.
Okay.
So either complete the first shell and look like helium, complete the second shell and look like neon, complete the third shell and look like the argon, the fourth shell look like krypton. They basically all want to get to a stable configuration. And either they give away electrons to get there, like lithium, they give away their only electron in the second energy level and fall back to helium. Or like fluorine, they steal an electron from somebody else and they become slightly bigger and look like neon. All of them want to get to a stable, filled outer shell configuration. And that's basically the story of chemistry right there. They all want to get to completely filling their outermost shell. And once it's filled, that's a stable configuration and they achieve chemical nirvana. And you can see that with all of these elements here, it basically, like carbon, nitrogen, oxygen, they all want to get to 8. They all want to get to 8 in the outer shell. So we've got room for 8 electrons in the second energy level. And they all want to get 8, either by giving electrons away or taking them or sharing them or something. They want to get 8 out there. And that's why 8 is the sort of magic number for chemistry, because they all want to fill their second shell completely. So what does this mean? What does all this mean? Let's look at electron configurations and orbital diagrams. So like I mentioned before, the electron configuration is just very simple, telling us where the electrons are. So we just give it N, what shell it's in, and then L, what subshell it's in, and then how many letters, how many electrons are there? 2, 6, 8, 3, however many there are. So that's it. Just shell, subshell, number of electrons. And that's the only information you get from an electron configuration. Now, an orbital diagram will give you more information concerning how much energy there are in those subshells. Now, an orbital diagram sort of just looks like a box or a line, depending on how you want to draw them. It sort of looks like this. So energy going up here, and then electrons here on the bottom. And so we give them either boxes or lines, either one, I don't really care. And then you individually show each electron and where they are and what spin they have. So I'll give you an idea of what I'm talking about. Here's lithium. So our energy goes up. As we go up the diagram, the energy gets higher. So N equals 1, N equals 2, N equals 3, and so on. And then each individual subshell's energy. S is the lowest, P is next, D is next, and then F is the highest. Lithium's only got 3 electrons. That one's fairly easy to put in. So the lowest one is always going to be 1s, always, 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 always. Next one is always going to be 2s. And remember, it's the diagram with the diagonal lines that tell us the order. So you don't have to memorize it. Make your little diagram and put the order that they go in. You can even have you can either just make the diagram and have it with you at all times when you're taking tests or whatever. You don't have to keep writing it out every single time. Just make one or print one out if you want to. So remember the different rules. First, we always put the first electron in order, whatever's the lowest energy. 1s is the lowest energy. So our first electron goes there, and it's always spin up. First one into an orbital, always spin up. Second one, spin down. Now, this is completely filled, no more room for electrons. So the rule is, remember, we go to the lowest energy level that isn't filled. This one's filled, no more room for electrons. What's the lowest energy level after that? 2s. And our 1 electron goes in, spin up. So this would be an orbital diagram. So if I ask you for an orbital diagram, this is what I'm looking for, not the electron configuration. The electron configuration is just 1s2, 2s1. That's it. It's got 3 electrons, and this is where they are. The orbital diagram is really useful when we're looking at how its electrons are being shared with another element for a covalent bond, or how its electrons are being either given away if it's a metal, or if its electrons are being taken in if it's a non-metal, to explain how many and where they go. The electron configuration isn't quite, it's pretty helpful, but the orbital diagram gives even more information that helps us like that. Any questions about the difference between an orbital diagram and electron configuration? Everyone's still scratching their head so far. Okay, wait till we get to the periodic table, and all will become known.
What is this called?
What are you doing?
Like, wait. What is this called?
Oh, yeah, it's the electron dots. Yeah, we're gonna get to that.
Okay.
Yeah. Okay. So again, let's have a look at the electron configuration and how reactive they are. So, hydrogen. What kind of ion does it form? +1, sometimes -1, usually +1. Usually gives this electron away and just becomes a proton with a plus charge. Or it can add an electron and then look like helium when it's minus. So it either gives its electron away and becomes just a proton, or it takes in another electron and then has a full shell like helium does. Lithium desperately wants to give away that one outer electron. When it does, looks like helium. So it is super active. It's an alkali metal. Remember, when you take these and throw them into water, boom, because they desperately want to give away that it has only one electron in its outermost shell. When it gets rid of it, it achieves nirvana. It now has a full shell, stable. And then we keep going, we keep adding electrons, and then notice when we get to fluorine, it's, as I mentioned before, it's almost full. It almost has a full set of electrons in its outermost shell. So it desperately wants to add another electron there to achieve stability. That is why fluorine is the most active element at stealing electrons from other elements. It is the best. It is the Mac Daddy of stealing electrons from other elements. Why? Because it's small. Its nucleus, the number of electrons it has, is close enough to the nucleus that the nucleus pulls on those electrons really tightly. And so it pulls on other elements' electrons too, and fills this gap. And once it fills that gap, now looks like neon, and it has achieved chemical nirvana. Same with sodium. Sodium and fluorine both want to achieve the electron configuration of neon. They have two different ways to do it. Fluorine steals an electron to fill this outermost shell. Neon, or sodium, is one more than neon. It has this, that's the only electron it has in its outermost shell. And we'll see later on, as we add shells, the distances, I think we saw this before when we were talking about the distances of the electrons away from the nucleus. As we add a new shell, you remember the first one was about 60 picometers and the second one was about 250. Then the third was like 650 or 700 picometers away. It was much, much further. And so that pull on those electrons that are really far away are much less because they're so far away. So sodium easily gives away that only electron in its outermost shell. It's far, much further away from the nucleus than the electrons, either in 1 or 2. 3 is much further away. So it gives that electron away easily, and also looks like neon. Magnesium has 2 electrons in its outermost shell. That's why it's always magnesium plus 2. So it gives away both of those, and then it looks like neon. So what you'll see is that as we look at how the electrons are organized in each one of these atoms, basically they all want to get to noble gas. They all want to look like neon or helium. They all want to look like neon. They all want to look like argon. They all want to have a full outer shell. And there's just different ways to get to it, either by sharing electrons so they fill it, giving electrons away so that they dump the electrons in their outermost shell, and now the second one in is now filled, or they steal electrons from somebody else and fill it. In all these situations, they all want to get to a full shell of electrons. Okay? Let's look at...
Professor,
Yes.
does this mean that like elements that only need one electron are the most reactive?
Yeah, the ones that have just one, that's why the alkali metals are so reactive, because they only have, whoops, let me go back. They only have a single electron in their outermost shell, only one. And so they desperately want to give that electron away. And then once they've given it away and become positively charged, they have a full shell. And that's why they become more and more and more reactive as you go down that group, because the elements get bigger and bigger and bigger. And so the distance between that single electron in its outermost shell becomes further and further and further. And so it becomes easier and easier and easier to give that electron away as you get bigger and bigger and bigger. So by the time you get out to like something like francium, that single electron is really far away from the nucleus, and it's given away like extremely easily. And so it's even more reactive. So sodium explodes, but as you go down, they explode even better. Like, you know, if you can get your hands on some rubidium, it explodes real good, even better than sodium does. So here's, if you, this is what arsenic looks like. So this is an orbital diagram, and we build them up one at a time. We fill them all up. And so you can see this particular example, we fill 3D before we get to 4P because of the difference in energies between D and P. D is a higher energy than P. So even though this D subshell is in a lower energy level, its energy is still higher. And so we fill this one before we completely fill, we fill 4S before we fill 3D. So it's not always in the order you think. That's why it's important to have that diagram with the different orbitals and our lines going through it to make sure we remember the order that they go in. Okay.
So when it forms ions, it still forms -3.
Yeah, arsenic is a metalloid, so it has both non-metal and metallic properties. You can see that, yeah, it could give away 3 electrons or gain 3 electrons, either way to sort of, but even if it gave away 3 electrons, it would still have these 2 in the outermost. So that's why it's sort of in between a metal and a non-metal.
Okay.
So finally, let's get to the periodic table, because as I mentioned many times, the periodic table will tell you everything you need to know. So here's our periodic table. And it looks different from your regular periodic table, because in this one, we've added the lanthanides and actinides. So these are the ones that are usually put on the bottom so that the periodic table doesn't look, you know, will basically fit on a printed page. That's the reason why we don't have, the periodic table doesn't look like this. But this, if you look at the periodic table, it will tell you exactly the order in which we fill electrons, just by going across the different periods. So as I mentioned, the first period has just 2 elements in it, hydrogen and helium. That's it, going from left to right. That is our 1s, 1s2. Then come all the way around again, starting with lithium and then going all the way across. Lithium, beryllium, and then we go all the way across. And there's room for 1, 2, 3, 4, 5, 6 more. Then we run out of space, go all the way back. Now we start with S again. Sodium, magnesium, and then go across, and we run into the P group. 1, 2, 3, 4, 5, 6. So you can see that these, the elements are broken down into blocks. And just by looking at the periodic table, you can see how many electrons go into each block. The S block has 2 families in it. The P block has 1, 2, 3, 4, 5, 6 families in it. The D block has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ah, interesting. And the F block has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So not only does it tell you how many electrons are in each subshell, it will also give you the order. All you need to do is just go across the periodic table and you can fill it in for yourself. So 1s1, 1s2, 2s1, 2s2, and then I go to 1s1 or 2s2, 2s2, and then this is 2p1, 2, 3, 4, 5, 6. And then once it's filled, I have a noble gas. Once it's filled, I have a noble gas configuration and everything is completely filled. There's no more chemical activity because it is a full shell. It does not want to give away any electrons. It does not want to take any electrons. It has a full complement of electrons. That's why they do not interact with other elements for the most part. We'll find out later that these really big noble gases like xenon, they're so big that fluorine is strong enough at pulling electrons away. It can even pull electrons away from a noble gas like xenon. That's how good it is at pulling electrons away. It can pull electrons away from the most stable elements there are. So fluorine is super good at stealing electrons away and achieving that noble gas formation electron configuration for itself. So any questions about this? This is, I know you haven't sort of seen the periodic table like this, but like I said, the reason why the F block elements, the actinides and lanthanides are sort of pushed down is because if we didn't, the periodic table would just be insanely wide. But even with them out of there, you can see that they're grouped into 2, 6, 10, and 14. And the reason, S, P, D, and F. And it was this, when people started, like Schrodinger's ideas seemed pretty crazy at the time, right? But then when they took a second look at the periodic table and saw that, oh my God, there's 2, 6, 10, 14 elements, like, oh, he's right. He's right. So now we're gonna have to pay attention to all these crazy, formulas he's come up with, because it explains precisely the chemistry that we see in the periodic table. And this is what basically cinched it for Schrodinger, when it was basically applied directly to the periodic table as we know it. And then he won his Nobel Prize. So again, different look. These are, remember, valence electrons. Who can tell me the difference between the core electrons and valence electrons? Anybody but Raymond. Who can tell me the difference between them? How come we're talking about valence electrons here? How come we're not talking about all electrons? What's the difference? I'll check the chat. So what do you think? What's the difference between them? How come we're talking about valence electron? What is a valence electron?
It's an electron on the outermost shell.
Exactly. Yeah, very good. Yeah, it's the electrons that are the furthest away from the nucleus. They're the ones involved with making bonds, either ionic bonds by being given away or being stolen, or covalent bonds where they're being shared. It's only the electrons in the outermost shells that are involved. The innermost shells are filled. They're not going to get involved with sharing or stealing. They're completely filled. Those are the core electrons. They're completely filled. they already look like noble gases. So they ain't getting involved with any of that chemistry nonsense because they're completely filled up. It's the valence electrons, which are the furthest ones away, that aren't complete. You do not have a complete set. So you can see from here, just looking at this, at the way we balance these out, that in the S block, this group is going to have 1 valence electron. This group is going to have 2. And then we move over to the P block. This group is going to have 3, 4, 5, 6, 7. And finally, once we get to the noble gases, they have 8, except for poor little helium here. It only has 2. But they have 8. So they're filled. That's a completely filled shell. Then we go back. And then once we have filled that 8, we go back to 1, 2, 3, 4, 5. So you see there's a pattern that repeats itself over and over and over. So why does these elements in the P block look like each other? Why do they have similar chemical properties? Well, as we go down the group, they have the same number of electrons in the P subshell. They all have 2 or 3 or 4 or 5. They all look the same. Chemically, I mean, electronically, they all look the same. They're just slightly bigger. But basically, you're getting the same flavor in the outermost shell. They're identical in the outermost shell. They have the same number of electrons, and they have them in the same subshell. So chemically, they react very, very similarly. Only difference being that those electrons are further away from the nucleus. And we'll see a little bit later that that makes a difference. That makes a difference in how reactive something is. The reactions that they undergo are the same, but how fast they undergo them or how often they undergo them will change slightly based on how far away they are from the nucleus. Yeah, so again, 2, 10, 2, and then 6, and then 10, and then 14. If you ever forget, for some reason, how many electrons are in each subshell, just look at the periodic table and immediately it will tell you. Just go across from left to right, 2, 6, and then 10, and then finally 14. And that also shows you when they're filled. We fill up S first, and then as you go across, then we fill up P, then we go down, then we fill up D. And only when we get to the 4th energy level do we finally start putting electrons in the F subshell, okay? And then this just gives you a different way of looking at the valence electrons. So just as I mentioned before, the reason why the elements in each one of these groups react so similarly is because they have the exact same valence electrons. Valence electrons in the 2p4, valence electrons in the 3p4, valence electrons in the 4p4, and the 5p4, and the 6p4. They all look very similar to each
Excuse me.
other. Yes.
Why there are 3 columns for 8b?
Because here, we'll learn a little bit later that here, when we get into we're filling up the D subshells, that a half-filled D subshell, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that is a stable configuration. And that when you're filling up the D subshell, sometimes you will fill up the D subshell halfway and then start adding electrons to P or F before you start putting new electrons into that shell. So it's when you get sort of in halfway in between. Notice that when we get to D5, that is halfway filled. We call that a semi-stable configuration. And so the next electrons after that can go into different places. And so 8b, those elements have a lot in common with each other. Like those are called different groups. Like there's the platinum groups of elements and the iridium group of elements and that sort of thing, because they're chemically very similar.
Okay.
So notice that when we're drawing these diagrams, that each of the orbitals in a particular subshell all have equal energies to each other. So all these p orbitals and all these d orbitals all have equal energy. So when we fill them in one at a time. 1, 2, 3, 4, 5. And we can put them, basically we can put them anywhere. We fill them in one at a time before going back, okay? So before we go, let's do just a couple questions to review. So, what are the quantum numbers? This is basically what we're going to be doing with our recitation this afternoon for my group, sort of reviewing some of this stuff. So, what are the 4 quantum numbers and names of the orbitals in n equals 4? So what are the how many different subshells are there in the n equals 4 level? And I'll check the chat to see how you. So think, what are the possible values? So if n, oops, let me clear that out. If n is equal to 4, so the principal quantum number is the same as the shell. How far away from the nucleus is it? So if n equals 4, that immediately tells you what L can be. L is equal to 0 to n minus 1. So it's 0, 1, 2, 3. So it has all the subshells in it. So what are they? How many electrons can you put in each one? Like, what are our possible m to the L values for the So what are our first of all, what are the subshells possible in this one? Do you want to tell me what subshells are possibly there? Now remember, we're in n equals 4. We're in the 4th shell. So how many subshells can you have in the 4th shell? No, right, one more. Yeah, one more, Rye. SPD, and what's the last one? Yep. So we can have, so n is 4, and so L, as I mentioned, goes from 0 to n to minus 1. So 0, 1, 2, 3. So L, that refers to S, P, D, and F. So basically, as soon as you get to level 4, you get to the 4th level, all the 4th shell, all the subshells are now available to you. You have S to fill, P to fill, D to fill, and F to fill. So how many electrons in each one? How many electrons can we put in S? Man, you guys are going to make me read the chat. Yes, Ryan, 2. All right, I'm going to put the chat down here. There we go. So 2. What about the P? 6. Very good, Ryan. D? Raymond got in there fastest with 10. And then what about F? Ryan in there with 14. That's right. And then the way we remember this is since L is equal to 0, 1, 2, and 3, those are the subshell letters. That's the subshell designation, 0, 1, 2, and 3. Orbital designation comes next. Remember, we have 4 quantum numbers: shell, subshell, orbital, spin. Those are our 4. So if this is our subshell number, our orbital number is based on the subshell number. Now the orbital's total number is given by negative L to positive L. That's how many they have. Well, if L equals 0, there isn't any negative 0 or positive 0. There's just 0. So that's 1 orbital. And that's its address, 0. When we get to P, -1, 0, +1. So that gives us 1, 2, 3 orbitals. And remember, each orbital has room for dose electrons. So 6. So this is our orbital address, or orbital number. When the subshell number is 2, how many is that? I can't remember. 2, remember, think of 2. Oh, right, I go from -2 to +2. So -1, 0, +1, +2, that's, oh yeah, that's 5. How many electrons can go in each one? 2. How many is that? 10. Oh, right. So remember, this is the N. Where are we? That's the shell. L, that's the subshell. M to the L, that's the orbital. And then M to the S, that's the spin inside each one. So, good work. Let's see if we were right about all this. Yeah, so the total, remember, if you ever want to know the total number of orbitals, just take the N, the shell, out to 4, and then just square it. So 1 squared, 2 squared, 3 squared, 4 squared. That gives you the number of orbitals. And then just multiply that by 2 to give you the number of electrons. Okay? So why don't we stop there? Do we have any questions? We're gonna keep going on this and sort of just drill it in and drill it in. Hopefully it made a little bit more sense today now that we looked at the periodic table, because now we're going to start really showing you, once we write out the orbital diagrams, it'll explain very well why some things are ionic, why some things are positively charged, some things are negatively charged, and some share electrons rather than giving them away or stealing them. And be able to predict that just based on the orbital diagrams. Yes.
So why would it be more stable to have a full shell instead of full subshells?
Your subshells are full when you have a full shell.
I mean, I still don't get why carbon cannot have like full 2 S's.
Because your second shell is not filled if the S is filled. Because there's room for 6 more electrons. So it's not a full shell. It's not stable.
Okay.
Yeah, there's room for 6 more. That is when the second shell is stable, when all the subshells are filled. Yeah, when we get further away, you will see that the transition metals will do that, but not something small as carbon.
I mean, we would have more energy to lose 4 electrons than 2 electrons.
Yes, but those 4 electrons are higher energy electrons than the 2. The ones that are in the p orbital are higher energy than the ones in the s. So it would lose those first.
Okay.
But carbon doesn't lose electrons. It becomes, if it becomes an ion, it becomes an anion. Very rarely does it become a cation.
Okay.
Very rarely. In fact, I can't think of when it does. I mean, it must be possible. I don't, my knowledge of carbon chemistry is not, I don't have a PhD in organic chemistry, so I can't tell you. But I don't think it forms a cation. I mean, it might, but I doubt it. Okay, any other questions before we go? We'll learn a lot more about this. Oh, yes, go ahead.
What
Yes.
would happen if n was above 4? Like, what if n was 5?
If n
And
is
how would we
5,
calculate it?
then we have the same SP, D, and F. We don't need any subshells bigger than F, basically to fill the entire periodic table. And so that's one. So once we get to 4 and 32 electrons, 5 is 32 electrons, and 6 is 32 electrons, and 7 is 32 electrons. We don't need any more in order to fill the periodic table. So I said before, if we build bigger elements that have, like, you know, a ton more electrons, we might find that they're organized into something different. But for now, F is the biggest orbital we need.